Welcome back to our second section on probability. Today we'll continue working with probability by looking at probability simulations. We'll learn about permutations and combinations, and then we'll also work with probability using combinatorics, which are permutations and combinations. We'll learn different ways to model probability situations, count possible outcomes, and use those outcomes to calculate probabilities. Let's take a look at our first example on simulations. And these simulation problems are fairly straightforward. I would say that they are very close to just some basic probability questions that you've probably seen before. So this says a cereal company is putting one of three prizes in each box of cereal. The prizes are evenly distributed, so the probability of winning any given prize is always 1/3. Mohammed wonders how many boxes he should expect to buy to get all three prizes. So he did 24 trials of a simulation, and his results are shown below. And every dot represents how many boxes that it took him to get all three prizes in that trial. It says use the results or use his results to estimate the probability that it takes more than three boxes to get all three prizes. And it just says P more than three boxes or probability that it's more than three boxes. And so it's here we have the number of boxes that were used. And it looks like there's 3 boxes, 4, 5, and so on. So if we look at all of the numbers that are greater than 3, that would include all of these data points here. And so we're going to count up those data points um, and determine what our probability is. So here we have 15 data points, it looks like. If we count all these blue dots up here, we get 15 data points. It says he did 24 trials. That means there's 24 blue dots total. So 15 over 24. And we're just going to leave that as our final answer for our fraction, for our fraction of our probability that it took him more than 3 boxes to get all 3 prizes. 15 over 24 is our answer for that one. And so a simulation is just a way to model a probability situation by repeating a random experiment. And then the results of these simulations, we can use them to estimate probabilities, and we can compare those results to what we would theoretically expect to happen. So that's what these problems are about. We're going to do just one more of these because I think they're fairly straightforward. Um, this says the probability that Leon makes a 3-point shot in basketball is 15%. For practice, he'll regularly shoot a series of these shots until he makes one. He's curious how many shots it will typically take him to get his first successful shot. And he simulated 25 trials of 3-point shots where each shot had a 0.15 probability of being made. And in each trial, he counted how many shots it took to get the first successful shot. It says use his results to estimate the probability that it takes more than 5 shots to get his first successful shot. Okay, I think there's a bit of extraneous information here. Um, the, the fact that he has a 15% chance of making that shot, I don't think that really determines whether or not he uh, gets a successful shot, because we just want to know the probability that he makes more than 5 shots given this information on the trials that he did. Um, and so all these blue dots indicate that he made the basket. So the 15% of him making that doesn't really make the blue dot uh, relevant or not. So that's extraneous information. We're going to cross that out. I need that. We're just looking at the blue dots here. It says the probability it takes him more than 5 shots. So here's at 5 is here. So all of the blue dots that are more than 5 would be all this information here. And so if we count all those, we get 13 blue dots there. That's more than 5 shots out of 25 shots. And so our fraction for the probability that it takes him more than 5 shots to get his first basket made is 13 out of 25. All right, next we're going to talk about permutations. Permutations are arrangements of objects where order matters. And we use permutations when we want to know how many different ways we can select and arrange items from a group. So if changing the order creates a different outcome, then we're dealing with a permutation. So this is our first formula, permutations, when order does matter. And this exclamation point is called a factorial. And we'll go over how to use factorials in our example here. But n is the total number of available items that there are, and r is the number of items that are being selected or arranged. Actually, I'll tell you what a factorial is just now, I guess. A factorial is we multiply the whole number by every positive whole number below it all the way down to 1. So an example would be if we looked at 5 factorial, that's equal to 5 times 4 times 3 times 2 times 1. And we just write the multiplication, one whole number previous, and keep the multiplication pattern until we get to 1. So that's what a factorial is. And we have that on our calculator also if you need to use your calculator for some of these, if that helps you. But I'll show you guys also a way that you can cancel out factorials and save yourself some time. Okay, so here's our first example. It says a swimming coach needs to choose a team for a relay race, and the coach must select 4 of 6 available swimmers and put them in a strategic sequence. It says, how many unique ways are there to arrange 4 of the 6 swimmers? So we're going to start by identifying what N and R is. So we have a total of 6 swimmers. That is N, our total amount. And then the number that we are going to arrange is 4. So R is equal to 4. And then we're just going to plug in these numbers into our factorial formula. So NPR becomes 6P4 is equal to 6 factorial over quantity 6 minus 4 factorial. So now this is 6 factorial over 2 factorial. And that's 6 times 5 times 4 times 3 times 2 times 1. And 2 factorial is just 2 times 1. And so we're going to cancel out the 1s and the 2s. So now we just are left with 6 times 5 times 4 times 3. And that's 360. There's 360 ways that he can choose a team of 4 people out of the 6. It's a lot of different ways. Now, another way that we can write this in a shortcut method is I'm just going to rewrite it like this and show you how you can rewrite this to cancel out factorials. So we could have written it like this, times 2 factorial, and then this 2 factorial on the denominator, and our factorials cancel out just like how a whole number would on a fraction. Okay. This next problem doesn't ask us to use the formula. It just asks us to identify what N and R is. So it says Jose is on a game show. It involves a taste test. He gets to see a list of 15 secret ingredients before tasting 3 dishes one after the other. The 3 dishes are all identical to each other, except that each dish contains 1 of 15 secret ingredients. He gets 60 seconds to identify what secret ingredient was in each dish. And it says we can use permutations to find the number of unique ways to arrange the ingredients in the dishes. What are the appropriate values of N and R? So N is our total. So our total number of dishes is, or excuse me, we have 15 secret ingredients, not dishes. We have 15 secret ingredients. And he's going to be tasting 3 dishes. So we're going to select 3 dishes out of the 15 secret ingredients. So that's all this question is asking us to find, is that N is 15 and R is 3. We're choosing 3, or excuse me, we're choosing R, which is 3 dishes. All right, we'll do one more example with these. 5 runners need to be arranged in 5 lanes for a race so that there is a runner in each lane. How many unique ways are there to arrange the runners in the 5 lanes? So we have 5 lanes and 5 runners. So in this case, N is 5 and R is 5. So this becomes 5p5. That's 5 factorial over 5 minus 5 quantity factorial. This is 5 factorial over 0 factorial. And this is a new rule here. 0 factorial is equal to 1. It's going to write it fairly large over here, so we have that as a rule. 0 factorial is equal to 1. Okay, and now this is 5 factorial. That's 5 times 4 times 3 times 2 times 1. And we'll just put that in the calculator. We get 120. 120 is the same thing as 120 over 1. So there's 120 ways to arrange those 5 runners into 5 lanes. Okay, factorials can also be used in some probability problems where there are many possible arrangements, and we'll see some examples of how this works in just a few minutes. Before we do that, though, we're going to go over another very similar topic, combinations. So permutations, make sure you have the permutations formula written down and that order matters. That's the key idea for permutations. For combinations, the order does not matter, and we have a slightly different formula for combinations. We still are using factorials, but we use combinations when we want to know how many different groups we can select from a larger group. Again, this is different from a permutation where with permutations, order does matter. A way that helps me to remember what permutations and combinations are in terms of which is which, does order matter or does it not, is a real world example of a combination lock. Technically, a combination lock is a permutation lock. With permutations, the order of the numbers matters. If we had a code on our combo lock and it's 1, 2, 3 for the lock, if you put in 3, 2, 1 for your combination on your combo lock, the lock isn't going to open. It has to be 1, 2, 3. It's the same 3 numbers, but they're in the wrong order. So really, it should be a permutation lock instead of a combination lock. So with a true mathematical combination, 1, 2, 3 is the same thing as 3, 2, 1. It would be considered the same selection. So I thought that's kind of an interesting way to remember permutations and combinations, that a combination lock really should be a permutation lock. And if you can remember that when you put in a combination in a combo lock, it has to be in the right order. That'll help you to remember the difference between these two ideas. All right, let's take a look at an example for this one. Elena is managing a construction project. She has 7 workers available to work on a given day, and she needs to select 5 of them. How many different sets of 5 workers can Elena choose? So 7 total, n equals 7. R is equal to 5. And so we're just going to write this as 7 choose 5. N factorial is 7 factorial. R factorial is 5 factorial. N minus R factorial is 7 minus 5 quantity factorial. 7 factorial over 5 factorial times 2 factorial. We can write the numerator as 7 times 6 times 5 factorial over 5 factorial times 2 factorial. And now we can cancel out the 5 factorials. And now we're left with 42 over 2 factorial, which is just 2 times 1, which is the same thing as 2. 42 over 2 gives us 21. So there's 21 different um, ways that she can pick these different groups of 5 workers. Okay, we're going to do just a couple more of these, and then we'll jump into probability problems with combinations and permutations. Simon is creating a flower arrangement. A client asked him to select 4 of the 7 available flower options to create the arrangement. How many different groups of 4 flowers can Simon choose? So he's going to choose 4 of the 7. So 7, choose 4. And again, we're just plugging these numbers in to our combinations formula and simplifying. So this is 7 minus 4 factorial, 7 factorial, 4 factorial times 7 minus 4 is 3 factorial. So now this is 7 times 6 times 5 times 4 factorial, and I'm stopping at 4 because that's our largest value on the denominator. So you have 4 factorial times 3 factorial. Our 4 factorials cancel out. Now this is 7 times 6 times 5 over 3 factorials, 3 times 2 times 1. So our numerator becomes 7 times 6 times 5 is 42 times 5 is 210. And the denominator is 3 times 2 times 1 is just 6. And it looks like we're going into our next example problem. So we're going to stop there as it's 35. 35. 210 over 6 is 35. Okay, our last example problem on combinations. This one doesn't tell us the total number of toppings from the word problem. We have to look more carefully for what n is. It says Mackenzie's ice cream shop lets customers choose 2 toppings from the list below to add to their ice cream. How many groups of 2 toppings can go on the order of the ice cream? Well, it doesn't matter the order of ice cream toppings. They can go in any order. They'll still be on the ice cream. So we're going to use combinations for this. And we're choosing 2 toppings out of 6. So this is n is equal to 6, r is equal to 2. 6 choose 2 is equal to 6 factorial over 2 factorial times 6 minus 2 factorial. 6 factorial over 2 factorial times 6 minus 2 is 4 factorial. 6 times 5 times 4 factorial. It's going to go on our numerator, and the denominator is 2 factorial times 4 factorial. Those 4 factorials are going to cancel out. Numerator is 30. Denominator is 2 factorial, which is just 2, and we get 15. Okay. Our last section is on probability with permutations and combinations. And so for these problems, we have to determine if we're using a permutation or a combination. I think that's one of the more challenging parts to this. But I wrote out the steps for you all to see how to solve these. So step 1 is we want to determine what the denominator is. Because we're dealing with probability, it's the probability, didn't write this because this is just basic probability. The probability is the number of favorable outcomes. I'm just going to write favorable outcomes over the total possible outcomes. And so the first thing we want to do is find the denominator. We want to figure out how many total possible outcomes are there. And this is where we have to decide if we're using a permutation or a combination. Then we want to find the numerator. This could just be 1. There could be only one way to get what we're looking to get, or there could be multiple ways to get what we're looking to get. So That could be the favorable outcomes there. Then we write the probability and we simplify or calculate what it is if we need to. So when we write the probability, we usually write it in terms of uh, NPR or NCR. And then we can simplify numerically if we need to. Let's take a look at the first one here. Adina sets up a taste test of 3 different waters. She has tap water, bottled water in glass, and bottled water in plastic. She puts these waters in identical cups and has a friend taste them one by one. The friend then tries to identify which water was in each cup. Assume that Adina's friend can't taste any difference and is randomly guessing. We want to know what is the probability that Adina's friend correctly identifies each of the 3 cups of water. Okay, so for our first step, we want to know what one outcome looks like. So we want to ask ourselves, what exactly is happening in one complete result? So for this problem, one outcome is a complete assignment of the 3 water types to the 3 cups. Each water has to be matched to the specific cup. So to count all the possible outcomes, we need to figure out, does changing the order or the arrangement create a different outcome? And here the answer is yes. So if we put tap water in cup number 1 and bottled water in cup number 2, that's different from switching them. So the order matters. We're going to use a permutation. So we have 3 types of water and 3 types of cups. And so our permutation for our denominator is 3P3. So that's our denominator. Now we're going to count how many outcomes are successful. So the friend has to get every single cup correct. There's only one arrangement where all 3 cups are correct. So there's only one way to do that. That's 1 on our numerator. And so that's our probability. And we could simplify 3p3 using permutations. And we're not going to do that. We did that already with enough examples, I think. But that is equal to 6. So these are equivalent statements. That's how we would write the probability there. So this is going to be A for this one. We're going to do a couple more of these because I think these can get a little bit tricky. So our next one is about ingredients. Sophie claims to be a tasting expert. To test her abilities, someone bakes Sophie a cake using 3 of the following ingredients. Sophie's challenge is to identify which set of 3 ingredients was used in the cake. Suppose that Sophie is just randomly guessing. What's the probability that Sophie correctly identifies the set of 3 ingredients in the cake? Okay. So for step 1, we're going to figure out what is happening in one complete result. So one outcome is a set of 3 ingredients chosen from the 6 available ingredients. Sophie only needs to identify which 3 ingredients were used. Now we're going to count all the possible outcomes. So we need to ask ourselves, does changing the order of these ingredients or the arrangement create a different outcome? For example, is coffee, vanilla, and ginger the same thing as ginger, coffee, and vanilla? And it is. It doesn't matter the order that we do this in, so we're going to use combinations. And so there's 6 total, and we're choosing 3. That's going to be our denominator. Now we're going to count how many outcomes are successful. Sophie has to identify the exact set of 3 ingredients that was used. There's only one correct set for this, so the numerator is 1 again for this problem. In our answer choices, we actually have to calculate what 6 choose 3 is. So let's go back and do that. So for our combinations formula, this is going to be 6 choose 3. That's going to be 6 factorial over 3 factorial times 6 minus 3 quantity factorial, 6 factorial over 3 factorial. Actually, I should write out. We'll do the denominator first. 3 factorial times 3 factorial. That's 6 times 5 times 4 times 3 factorial over 3 factorial times 3 factorial. One of those 3 factorials in the denominator is going to cancel with the numerator. And we get 6 times 5 times 4. That's 20 times 6, which is 120 over 3 times 2 times 1. That's 120 over 6. And it looks like we get 120 over 6 is equal to 20. So now we know this is 1 over 20. Okay, let's do one more example with where the denominator or where the numerator is not equal to 1. This one I think is a really tough example. So I really want to go over this one together before you do any practice with these. Nia is one of 24 students in her class. Every month, her teacher randomly picks 4 students from the class to be the class president, the vice president, the secretary, and the treasurer. No student can have 2 of the same positions. So every month, she picks 4 kids. There's 24 students in the class. Nobody can have the same 2 position. So we want to figure out what's happening in one complete result. So there's 4 students being assigned to 4 different positions. Each student is assigned to a specific position. So Nia as president and Bob as vice president is different than Bob as president and Nia as vice president. Because those are different, we're dealing with permutations. The order does matter here. Even though Nia and Bob both got picked for something, it's still a different outcome if Nia is president versus if Bob is president. Okay, so now we know we're dealing with permutations. So we can actually cross off answer choice B because that has combinations on it. So now we want to count all the possible outcomes. So we know that the order matters. We're going to use permutations, but now we need to decide what that's going to be. So for our denominator, that's going to be, we have 24 P4, or picking 4 students out of the 24. That gives us our denominator. Okay, now we want to count how many outcomes are successful, and this is the really tough part, I think. We want Nia to be president, so Nia's position is already fixed. So now we only need to fill the 3 remaining positions. So it just says, what's the probability that Nia is president? So the probability that Nia is president, there's 23 students remaining, and we're arranging 3 of them into the 3 remaining positions of vice president, secretary, and treasurer. So our numerator is going to be 23P3. Okay, so that's the probability that Nia is chosen as president, and that's just our final answer for this. That's going to be C. This question thankfully doesn't ask us for the numerical values of this. If it did, we could use the permutations formula. So I think the toughest thing about these problems is figuring out what the denominator is and if it's going to be a permutation or a combination. All right, just to summarize, permutations and combinations, they can help us count possible outcomes when we're finding a probability. So again, we use permutations when order matters, combinations when order does not matter. And then we put the number of successful outcomes over the total possible outcomes to find probability. And that's true for any type of probability. Okay, so that is everything on permutations and combinations and probability with combinatorics for this lesson.